हेलो स्टूडेंट्स, वेलकम टू एनसीईआरटी रीडर। तो इस वीडियो में हम लोग आज ये देखेंगे कि रेडिएशन जो कि हीट ट्रांसफर का एक इम्पोर्टेंट प्रोसेस है वो किस तरीके से होगा। तो रेडिएशन के लिए आपको ये पता होना चाहिए कि रेडिएशन जो है अ, ये हीट ट्रांसफर का ऐसा मोड है जिसमें कि मीडियम की जरूरत नहीं होती है। विदाउट एनी मीडियम इट कैन ट्रांसफर हीट फ्रॉम वन पॉइंट टू अनदर पॉइंट। जैसे सन से जो लाइट आती है हमारे पास, तो उसमें रेडिएशन का जो प्रोसेस है उसी के थ्रू आती है। तो रेडिएशन जो है ये सबसे फास्टेस्ट मोड है हीट ट्रांसफर का। और इसमें जो एनर्जी का प्रोपेगेशन होगा वो स्पीड ऑफ लाइट के बेसिस पे होगा, यानी कि जो स्पीड ऑफ लाइट है उसी स्पीड से जो है हीट एनर्जी जो है आपको एक जगह से दूसरी जगह प्रोपेगेट करेगा या ट्रांसफर होगा। दैट इज कॉल्ड रेडिएशन। और जो इम्पोर्टेंट पॉइंट है इसमें वो ये है कि जितने भी बॉडी रेडिएट एनर्जी कर रही है, अगर हम इस चीज को देखें कि कोई भी बॉडी का अगर हम टेम्परेचर को मेजर करेंगे तो मिनिमम टेम्परेचर कितना होगा, 0 केल्विन। तो 0 केल्विन से थोड़ा भी अगर ज्यादा टेम्परेचर है उस बॉडी का, तो वो रेडिएट कर रहा है एनर्जी को फ्रॉम द बॉडी टू द सराउंडिंग मीडियम। और रेडिएशन बॉडी का हम स्टॉप नहीं कर सकते। दैट इज वाई इसके पीछे का लॉजिक यही है कि उसका टेम्परेचर अगर वो 0 केल्विन से भी ज्यादा है तो वो रेडिएट कर रहा है, 0 केल्विन से भी ज्यादा है तो वो रेडिएट कर। दैट इज द थिंग वी नीड टू अंडरस्टैंड। एंड इसमें और जो समथिंग यू नीड टू नो अबाउट द परफेक्टली ब्लैक बॉडी। परफेक्टली ब्लैक बॉडी किसको बोलते हैं? तो सबसे पहले हम देखते हैं इसमें कि रेडिएशन जो रेडिएशन रेडिएशन के बारे में हमने आपको अभी जस्ट बताया कि ये हीट ट्रांसफर का एक ऐसा मोड है जिसमें कि मीडियम की जरूरत नहीं होती है। दैट इज द थिंग यू नीड टू अंडरस्टैंड। नो नीड टू रिक्वायर एनी काइंड ऑफ मीडियम। एंड द रेडिएशन का जो स्पीड होगा वो स्पीड ऑफ लाइट के बराबर होगा। और कोई भी बॉडी है तो उसका टेम्परेचर 0 केल्विन से ऊपर अगर होगा तो वो रेडिएशन कर रहा है और उसके रेडिएशन को आप स्टॉप नहीं कर सकते। ये तीन चीज आपके दिमाग में रहनी चाहिए। और नेक्स्ट जो इम्पोर्टेंट रेडिएशन के बारे में है, सॉरी, रेडिएशन से रिलेटेड चीजों को समझने के लिए वी नीड टू हैव आइडिया ऑफ द ब्लैक बॉडी। तो सबसे पहले रेडिएशन का जो डिफिनेशन है वो क्या है? द प्रोसेस बाय विच heat is transferred directly from one body to another without requiring any medium। ये चीज ध्यान रखेंगे कि इस मीडियम अगर नहीं भी है तब भी ये ट्रांसफर होगा। एनी मीडियम इज कॉल्ड रेडिएशन। दिस इज द फर्स्ट पॉइंट वी नीड टू अंडरस्टैंड। एंड देन सेकंड इज, ये तो डिफिनेशन हो गया। सेकंड, रेडिएशन द फास्टेस्ट मोड ऑफ हीट ट्रांसफर। रेडिएशन is the fastest mode of heat transfer। ये चीज ध्यान रखना है कि ये रेडिएशन जो है ये फास्टेस्ट मोड ऑफ हीट ट्रांसफर है। और हीट का जो एनर्जी का जो प्रोपेगेशन होगा, हीट एनर्जी is propagated with a speed of light। सो ये चीज आपके माइंड में रहना चाहिए। और जितने भी बॉडी है, ऑल बॉडीज रेडिएट्स एनर्जी, ये चीज भी है इंपॉर्टेंट। तो ऑल बॉडीज रेडिएट्स एनर्जी। इसके पीछे का रीजन क्या है कि एट ऑल टेम्परेचर। यानी कि टेम्परेचर जब भी आपको ग्रेटर देन 0 केल्विन होगा, तो उस केस में जो है वो उस बॉडी से रेडिएट करेगा। एंड एट ऑल टाइम्स what we can say, radiation from a body can never be stopped. Body can never be stopped. तो ये चीज ध्यान रखेंगे रेडिएशन के बारे में। अब सबसे पहले हम लोग देखते हैं कि परफेक्टली ब्लैक बॉडी क्या है। परफेक्टली ब्लैक बॉडी, जब परफेक्टली ब्लैक बॉडी का मतलब ये है कि बॉडी which absorbs all the radiations incident on it is called perfectly black body। तो दैट मीन्स कि ये चीज ध्यान रहे आपको कि परफेक्टली ब्लैक बॉडी वो बॉडी है जो कि सारे रेडिएशंस को एब्जॉर्ब कर ले। दैट काइंड ऑफ बॉडी इट इज कॉल्ड परफेक्टली बॉडी, परफेक्टली ब्लैक बॉडी। अब परफेक्टली ब्लैक बॉडी के लिए कुछ टर्म्स डिफाइंड है, जैसे कि एब्जॉर्बिड पावर क्या होगा, इमिसिव पावर क्या होगा, स्पेक्ट्रल इमिसिव पावर क्या होगा, एंड इमिसिविटी क्या होगा। These are the ratio to understand that what it is called absorb, which one is called absorptive power. So next, इसमें ये एक डिफिनीशन पॉइंट ऑफ व्यू से है कि एब्जॉर्प्टिव पावर क्या होता है, इमिसिव पावर क्या होता है। लेट्स सी दिस। तो एब्जॉर्प्टिव पावर को अगर हम लोग डिफाइन करते हैं, तो ये एक तरह से किसी भी सरफेस पे जो रेडिएंट एनर्जी एब्जॉर्ब होगा, उसके बेसिस पे वो किस टाइम इंटरवल में हो रहा है एब्जॉर्ब, एंड रेडिएंट एनर्जी जो इंसिडेंट हो रहा है, इंसिडेंट और एब्जॉर्ब इन दोनों का जो रेशियो होगा दैट इज कॉल्ड एब्जॉर्बिव पावर। और अगर ब्लैक बॉडी में ये हम देखें, तो ब्लैक बॉडी का एब्जॉर्बिव पावर जो है वो यूनिटी होता है, यानी कि मैक्सिमम होता है। मैक्सिमम जितना उस पे इंसिडेंट हो रहा है और जितना वो एब्जॉर्ब कर रहा है, वो दोनों इक्वल हो जाएगा, तो वो रेशियो 1 हो जाएगा। तो दैट मीन्स कि एब्जॉर्बिव पावर जो होगा of a surface is the ratio of the radiant energy absorbed। ये चीज ध्यान रखेंगे कि पहले एब्जॉर्ब है, न्यूमरेटर में जो होगा, जो एनर्जी एब्जॉर्ब हो रहा है उसके बेसिस पे रेडिएंट एनर्जी एब्जॉर्ब इन द गिवन टाइम इंटरवल। और इसमें डिवाइड करेंगे टू द टोटल रेडिएंट एनर्जी, टोटल रेडिएंट एनर्जी इंसिडेंट ऑन इट, इसको बोलेंगे एब्जॉर्बिव पावर। तो दैट मीन्स कि अगर हम इसकी बात, हाँ एक चीज ध्यान रखेंगे, सेम टाइम इंटरवल में, इन द सेम टाइम इंटरवल, जितना देर में एब्जॉर्ब हो रहा है उसी टाइम इंटरवल में जितना एनर्जी उस पे इंसिडेंट हो रहा है, उन दोनों का जो रेशियो होगा सेम टाइम इंटरवल। तो अगर हम बात करें एब्जॉर्बिव पावर इसका ब्लैक बॉडी का, तो वो मैक्सिमम होगा। सो एब्जॉर्बिव पावर ऑफ ब्लैक बॉडी इज मैक्सिमम, इज मैक्सिमम। और मैक्सिमम का मतलब है जितना उस पे इंसिडेंट हो रहा है और जितना वो उस पे एब्जॉर्ब एब्जॉर्ब कर रहा है वो बॉडी, अगर वो ब्लैक बॉडी है तो उसका दोनों का रेशियो जो है आपको वो इक्वल होगा, तो इट इज मैक्सिमम एंड दैट इज यूनिटी। So this is absorptive power you need to understand. Next, you have to understand that what is called emissive power. ठीक है, क्योंकि इसका यूज जो है कभी कभी एडवांस लेवल पे क्वेश्चंस में आपको पूछा जाता है, तो आपको पता होना चाहिए कि एब्जॉर्प्टिव पावर क्या है, इमिसिव पावर क्या है। तो नेक्स्ट इज इमिसिव पावर। इमिसिव पावर, तो इमिसिव पावर को अगर हम डिफाइन करते हैं तो इमिसिव पावर किसी भी सरफेस के लिए जो है, जो रेडिएंट एनर्जी इमिट हो रहा है पर सेकेंड और पर यूनिट एरिया, उसी को बोलेंगे इमिसिव पावर। तो दैट मीन्स कि इमिसिव पावर ऑफ ए सरफेस is defined as the radiant energy emitted per second per unit area of the surface। तो दैट मीन्स कि अगर हम रेडी इमिसिव पावर की बात करेंगे तो ये एक तरह से किसी भी सरफेस पे जो रेडिएंट एनर्जी इमिट कर रहा है पर सेकेंड पर यूनिट एरिया, उसी को बोलेंगे रेडिएंट सॉरी इमिसिव पावर। दिस इज ऑल अबाउट द एब्जॉर्प्टिव पावर एंड इमिसिव पावर। ठीक है, अब आपको समझना है इमिसिविटी क्या होता है। इमिसिविटी, इसको हम लोग ई से डिनोट करते हैं, इप्सिलॉन इस तरह से लिखेंगे ई। तो ये जो है आपको जो हमने अभी निकाला है कि एब्जॉर्प्टिव पावर और ये एब्जॉर्प्टिव पावर और इमिसिव पावर, तो इसमें आपको ये चीज ध्यान रखना है कि ये रेशियो होता है किसका, तो इट इज द रेशियो ऑफ इमिसिव पावर, it is the ratio of emissive power of a body to the emissive power of a black body। ब्लैक बॉडी, तो किसी भी बॉडी, अगर हम इमिसिव पावर ऑफ ए ब्लैक बॉडी से अगर हम डिवाइड कर देंगे किसी बॉडी के इमिसिव पावर पे, तो वो इमिसिविटी कहलाएगा। इट इज द रेशियो ऑफ इमिसिव पावर ऑफ ए बॉडी टू द इमिसिव पावर ऑफ ए ब्लैक बॉडी एट सेम टेम्परेचर, एट द सेम टेम्परेचर। एट द सेम टेम्परेचर। तो इमिसिविटी का जो रेंज होता है ये आपको 0 से लेकर के 1 के बीच में होगा। हमने अभी बताया था कि आपको अगर ब्लैक बॉडी होगा तो उसका इमिसिव पावर जो है आ, यहाँ पे सॉरी ये एब्जॉर्प्टिव पावर जो है वो मैक्सिमम होता है। और अगर हम ब्लैक बॉडी की बात करें तो उसके लिए, क्योंकि ये ब्लैक बॉडी ही ले लिया जाएगा और ऊपर में भी ब्लैक बॉडी ही रहेगा, तो ये इमिसिविटी 1 हो जाएगा। सो इमिसिविटी अगर 1 आपको आ रहा है रिजल्ट, तो दैट मीन्स कि दिस इज फॉर ब्लैक बॉडी। ब्लैक बॉडी किसको कहेंगे, ब्लैक बॉडी उसको कहेंगे जो किसी भी रेडिएशन को एब्जॉर्ब कर ले, दैट इज कॉल्ड ब्लैक बॉडी। किसी भी नहीं, ऑल रेडिएशंस को, ऑल काइंड ऑफ रेडिएशंस, ऑल काइंड ऑफ रेडिएशंस को अगर वो एब्जॉर्ब करते जा रहा है, तो दैट काइंड ऑफ बॉडी इज कॉल्ड ब्लैक बॉडी। एंड ऑन द बेसिस ऑफ दैट यू नीड टू अंडरस्टैंड दैट व्हाट इज इमिसिविटी। इमिसिविटी फॉर ब्लैक बॉडी इट इज 1। नेक्स्ट टू अंडरस्टैंड द नेक्स्ट, जो सबसे इम्पोर्टेंट और बार बार पूछा जाता है आपको जेईई मेन में और जेईई एडवांस में, यहाँ से आपका स्टीफेंस लॉ है। स्टीफेंस लॉ है और स्टीफेंस लॉ क्या है, लेट्स सी दिस। स्टीफेंस लॉ, स्टीफेंस लॉ जो है ये मेनली आपको इसके बारे में बताएगा, कोई भी ब्लैक बॉडी के बारे में बताएगा कि अगर ब्लैक बॉडी है तो उससे जो एनर्जी रेडिएंट हो रहा है, जो ब्लैक बॉडी है उससे जो एनर्जी रेडिएंट हो रहा है, तो रेडिएंट एनर्जी को टाइम और एरिया के बेसिस पे हम जानते हैं कि एनर्जी पर यूनिट एरिया जो होता है, एनर्जी पर यूनिट एरिया वो पावर होता है। सॉरी, एनर्जी पर यूनिट एरिया नहीं, एनर्जी पर यूनिट टाइम, पर यूनिट टाइम वो पावर होता है। और अगर उसको एरिया से ये कर दिया जाए, डिवाइड कर दिया जाए, यानी कि एनर्जी पर यूनिट एरिया पर यूनिट टाइम कह दिया जाए, तो ये कुछ नहीं, इंटेंसिटी है, इंटेंसिटी, इंटेंसिटी इट इज। तो रेडिएंट एनर्जी जो इमिट होगा परफेक्टली ब्लैक बॉडी से पर सेकेंड पर यूनिट एरिया, वो डायरेक्टली प्रोपोर्शनल होता है T⁴ के। टी मींस टेम्परेचर, एब्सोल्यूट टेम्परेचर इट इज। तो सबसे पहले हम लोग देखेंगे कि इसमें जो मेजर जो इसका डिफिनीशन है वो क्या है, द रेडिएंट एनर्जी इमिटेड, रेडिएंट एनर्जी इमिटेड बाय ए परफेक्टली ब्लैक बॉडी, परफेक्टली ब्लैक बॉडी पर सेकेंड पर यूनिट एरिया। इसी को हम लोग बोलते हैं इमिसिव पावर, is directly proportional to the fourth power of absolute temperature of the body। तो दैट मीन्स अगर हम इसको कैपिटल आर से डिनोट करते हैं तो कैपिटल आर जो है ये डायरेक्टली प्रोपोर्शनल टू T⁴ होगा। और अगर हम प्रोपोर्शनैलिटी को रिमूव करें तो ये जो है आपको सिग्मा T⁴ हो जाएगा। ये आर क्या है, रेडिएंट एनर्जी इमिटेड बाय परफेक्टली ब्लैक बॉडी पर सेकेंड पर यूनिट एरिया, दैट इज आर। आर, तो आर को हम बोल सकते हैं कि ये एक तरह से पावर बाय एरिया है। और पावर बाय एरिया को ही हम इंटेंसिटी, इसको समटाइम्स इट इज यूज्ड एज इंटेंसिटी आल्सो, इंटेंसिटी आल्सो। सो डोंट गेट कंफ्यूज, कभी कभी रेडिएंट एनर्जी पर यूनिट एरिया पर यूनिट टाइम बोला जाएगा, कभी इंटेंसिटी बोल देगा, तो उसमें कंफ्यूज नहीं होना है, वो इंटेंसिटी ही है। और इसको हम लिख सकते हैं यहाँ से, इट इज सिग्मा T⁴। अब अगर हमें पावर चाहिए तो पावर को कैसे निकालेंगे, पावर P हो गया, पावर जो हो जाएगा वो एरिया इधर से इधर मल्टीप्लाई हो जाएगा, तो सिग्मा एरिया T⁴, ये हो गया आपका पावर। कौन सा पावर, जो एनर्जी रेडिएट हो रहा है पर सेकंड किस रेट से हो रहा है, कि वही एनर्जी पर सेकंड को हम पावर बोलेंगे यहाँ पे। जहाँ पे सिग्मा वैल्यू जो है ये न्यूमेरिकल फिक्स्ड वैल्यू है, दिस इज सिग्मा कांस्टेंट, जो प्रोपोर्शनैलिटी कांस्टेंट है, एंड दिस वैल्यू इज 5.67 into 10⁻⁻8, and it will be watt meter -2 and Kelvin to the power -4. This is the unit of sigma, and this value is a fixed constant value, and it will be mentioned in the problem if it is asked you. तो जो अगर कोई भी बॉडी है, उस बॉडी के लिए नहीं, ये जो हमने लिखा है पावर, ये किस बॉडी के लिए है, ये तो ब्लैक बॉडी के लिए है। अगर कोई और बॉडी होगा तो उसके लिए हम लोग क्या लिखेंगे, क्योंकि जो टर्म हमने लिखा है दिस इज फॉर एनी काइंड ऑफ बॉडी, नो, दिस इज फॉर ब्लैक बॉडी ओनली। ऑलवेज रिमेम्बर दिस। ये जो हमने लिखा है ये ब्लैक बॉडी के लिए है, ब्लैक बॉडी, परफेक्टली ब्लैक बॉडी। अब अगर ब्लैक बॉडी नहीं है, कोई जनरल बॉडी है, कोई भी बॉडी है, तो उसके लिए हम लोग फॉर अदर काइंड ऑफ बॉडी क्या लिखेंगे? फॉर अदर बॉडीज, अगर बॉडीज ब्लैक नहीं है तो पावर को लिखा जाएगा, दिस इज सिग्मा, देयर विल बी वन टर्म, इमिसिविटी। इमिसिविटी सिग्मा ए टी टू द पावर 4। इमिसिविटी कहां से टपक पड़ा? तो इमिसिविटी अदर बॉडी में तो आएगा, ब्लैक बॉडी में तो 1 होता है, इसलिए उसकी जरूरत नहीं पड़ी। वेयर ई जो है यहाँ पे ये इमिसिविटी ऑफ द बॉडी है, इमिसिविटी ऑफ द बॉडी। तो इमिसिविटी ऑफ द बॉडी जो है ये होता क्या है, अभी तुरंत देखे थे इमिसिविटी ऑफ द बॉडी क्या होता है। इमिसिविटी ऑफ द बॉडी जो है ये रेशियो ऑफ इमिसिव पावर ऑफ ए बॉडी बाय इमिसिव पावर ऑफ ब्लैक बॉडी है, और इसका रेंज 0 to 1 होता है। ब्लैक बॉडी अगर है तो 1, दैट्स इट। तो इसमें कोई ज्यादा नहीं है। तो ये जब भी आप यूज करेंगे तो इन जनरल ये फॉर्मूला को अगर हम यूज कर ले और ई को 1 कर ले तो वो ब्लैक बॉडी के लिए हो जाएगा। तो ये फॉर्म ही मेन है जिसको आपको दिमाग में सेट करना है, और इसके बेसिस पे जो है आपको क्वेश्चंस पूछे जाते हैं। अब कभी कभी होता है क्या है, सिस्टम, कोई एक सिस्टम रहेगा उसका टेम्परेचर आपको दे दिया जाएगा और सराउंडिंग का टेम्परेचर दे दिया जाएगा, और उसमें बोला जाएगा कि रेट ऑफ हीट लॉस क्या है, रेट ऑफ हीट लॉस, दिस इज बेस्ड ऑन स्टीफेंस लॉ ओनली, स्टीफेंस लॉ ओनली। तो किस रेट से हीट को लॉस कर रहा है वो होता क्या है उसको हम लोग एक बार देखते हैं। तो दूसरा टैब इसमें आएगा आपको, वो है रेट ऑफ हीट लॉस, रेट ऑफ हीट लॉस। हीट लॉस का जो रेट है वो क्या है? तो मान लेते हैं कि हम कोई एक स्फेयर है, ये स्फेयर मान लिए, और इस स्फेयर का एक रेडियस मान लेते हैं, स्मॉल आर मान लेते हैं, और इस स्फेयर का टेम्परेचर टी मान लिए, और टी नॉट जो है ये टेम्परेचर सराउंडिंग का है। अब अगर इससे हीट जो है आपको लॉस होगा तो वो किस रेट से लॉस होगा, दैट वी हैव टू फाइंड आउट, दैट वी हैव टू फाइंड आउट। तो इसको डायरेक्ट अगर स्टीफेंस लॉ पे देखा जाए, सोचा जाए उसको, तो आप किस तरह से सोचोगे देखते हैं। फॉर ए स्फेयर ऑफ रेडियस आर एट टेम्परेचर टी placed in a surrounding of temperature T नॉट, T नॉट। तो इस केस में क्या होगा, अगर T आपका ज्यादा है T नॉट से तो इससे जो है हीट लॉस होगा। तो इसमें जो पूछा जाएगा आपको वो ये पूछा जाएगा कि द रेट ऑफ हीट लॉस ये क्या होगा, एज। तो इसको हम लोग लिखते हैं dQ/dt, यानी कि Q जो है टाइम के रिस्पेक्ट में जो चेंज कर रहा है दैट इज पावर ओनली। Q क्या है, एनर्जी, T क्या है, टाइम, एनर्जी बाय टाइम पावर देता है। तो ये पावर जो अभी हम लोग देखे थे स्टीफेंस लॉ में वो क्या था, वो था इप्सिलॉन सिग्मा ए टी टू द पावर 4, लेट्स सी इट इज इप्सिलॉन सिग्मा ए टी टू द पावर 4। अब तो टेम्परेचर यहाँ पे तो लॉस हो रहा है, तो यहाँ पे लॉस कितना होगा उसको निकालने के लिए आपको इसका एरिया जो है हम लोग चेंज कर देते हैं, 4πr² एरिया हो गया, और बॉडी का इमिसिविटी इप्सिलॉन हो गया, एंड सिग्मा जो है कांस्टेंट हो गया, देन टी टू द पावर 4 माइनस टी नॉट टू द पावर 4। ये टेम्परेचर में डिफरेंस जो होगा इसी से आपका यहाँ पे जो लॉस हो रहा है हीट का वो यही होगा, दैट्स इट। यही चीज दिमाग में लगाना था। यहाँ पे इप्सिलॉन जो है ये इमिसिविटी है किसका, स्फीयर का, या ये बॉडी जो है ये स्फेरिकल बॉडी का। तो इप्सिलॉन जो है ये स्फेरिकल बॉडी का क्या है, इमिसिविटी, इट इज इमिसिविटी ऑफ स्फेरिकल बॉडी। इस तरह का क्वेश्चन पूछा जाएगा आपको, ठीक है। लेकिन कभी कभी क्वेश्चन, इसी क्वेश्चन को थोड़ा मॉडिफाइड कर दिया जाएगा और जिसमें कि आपको डेंसिटी दे दिया जाएगा, किसका, स्फेयर का डेंसिटी दिया जाएगा, स्पेसिफिक हीट कैपेसिटी दिया जाएगा। तो उस टाइप के क्वेश्चन में जो टेम्परेचर का जो चेंजिंग होगा टाइम के रिस्पेक्ट में, वो क्वेश्चन पूछा जाता है। लेट्स सी इट इज, तो दिस इज कॉल्ड, दिस वाज व्हाट इट इज, इट वाज रेट ऑफ हीट लॉस। बट कभी कभी पूछा जाएगा रेट ऑफ कूलिंग क्या है, तो रेट ऑफ हीट लॉस पूछा जाएगा तो हम इसको यूज करेंगे, अगर रेट ऑफ कूलिंग पूछा जाएगा तो इसको यूज करेंगे। सो दिस इज द नेक्स्ट टाइप ऑफ क्वेश्चन, रेट ऑफ कूलिंग। रेट ऑफ कूलिंग, रेट ऑफ कूलिंग के लिए अगर हम यूज करते हैं तो मान लेते हैं कि यही एक स्फेयर है और इस स्फेयर का जो है रेडियस आर है और इसका टेम्परेचर टी है, यहाँ का टेम्परेचर टी नॉट है, और जो रेड स्फेयर दिया गया है आपको, इसका डेंसिटी जो है रो है, रो डेंसिटी। एंड इस स्फेयर का जो है स्पेसिफिक, दिस इज डेंसिटी हियर, डेंसिटी ऑफ द स्फेयर इज मेंशन्ड एंड दिस एस इज स्पेसिफिक हीट। इन सब का एक डेरिवेशन है बट आई एम राइटिंग जस्ट रिजल्ट ओनली। सो इस केस में जो है आपको दिस स्पेसिफिक हीट कैपेसिटी इट इज, तो इस केस में रेट ऑफ फॉल ऑफ टेम्परेचर जो होगा, द रेट ऑफ फॉल इन टेम्परेचर इज, इसको हम लोग लिखेंगे दिस इज डी टी बाय डी टी। टी, कैपिटल टी इज फॉर टेम्परेचर, स्मॉल टी फॉर टाइम। सो एट व्हाट रेट द, सॉरी, रेट ऑफ कूलिंग जो होगा इसमें क्या होगा, दिस रेट ऑफ कूलिंग इज, दिस इज माइनस ऑफ, we know that temperature is cooling here, that is why it is called minus. So it is 3, I'm writing result, epsilon sigma t to the power 4 minus t naught to the power 4 divided by rho sr, rho sr। तो ये फॉर्म आपको याद रहना चाहिए टू सॉल्व द रेट ऑफ fall, at what rate the temperature is falling. This is one of the important result which you need to remember to solve the question without solving. And once you will go for derivation, it is lots of time will be consumed over there. We don't have that much time in exam. And JMain kind of exam where the 2-minute, 3-minute questions are, you have the level of question is that only. So without remembering, it is very difficult to solve the question over there. And we think that question is tough. No, question is not tough. You have to remember the form final result it is, so that you can make the question easier and you can solve over there. So these are the things which you need to remember in case of Stephen's law. Then we have Newton's law of cooling. Newton's law of cooling. So this is the next topic in this one, Newton's law of cooling. Newton's law of cooling. Only 5-6 concept or what result you, if you remember, you can easily solve JEE main kind of question. For JEE advanced, you need to have go through the all derivations concept over there, but for JEE main only you need to remember the concept and some graph and some formula only, you can easily solve over there. It is not good. So this is Newton's law of cooling is the concept where you can see that temperature of a body is not much different from the surrounding temperature. There is very less difference. Less means 1 degree, 2 degree, 3 degree, 4 degree. Likewise, if the temperature of the body and the surrounding temperature is there, then what rate of cooling will be, that you can see here. This is the Newton who derived this relation when the body temperature and the surrounding temperature is not that much different. It is very nearby. It is that case how rate of cooling it is. So this is the first. This is just I'm writing the definition about the Newton's law of cooling. What is Newton's law of cooling? अगर किसी भी बॉडी का टेम्परेचर को हम मान ले, if the temperature of a body be T on T is not different from surrounding temperature. Surrounding temperature. Surrounding temperature, I am assuming here T naught. Then rate of cooling of a liquid is directly proportional to the difference in the temperature of liquid and temperature of surrounding. That is, you can say here, what the difference between the liquid temperature and the surrounding temperature, that rate of cooling will be directly proportional to it. So if you want to write the diagram of this Newton's law of cooling, Newton's law of cooling it is. So how you can relate it with the diagram? Let's see it is. We have x-axis and y-axis. Here this is body temperature. And on y-axis, we are having rate of cooling. Rate of cooling को अगर आप दिखाएंगे तो it is minus of dt by dx. Sorry, it is minus of dt by dt, where t capital is temperature and a small t is time. Minus means it is cooling, that is why it is called rate of cooling. So this kind of diagram you'll be having. This is what it is. This is rate of cooling graph with the temperature of the body. And in this factor on y-axis, you'll be having there is called y-intercept on this will be, this is K times of T naught. T naught is the surrounding temperature and a K is here constant. So if you write the diagram between rate of cooling and the temperature difference means T minus of T naught. T is the water liquid temperature and T naught is the surrounding temperature. And on a y-axis, it is rate of cooling. So it is dt by dt. So in that case, you'll be getting that line which is passing through origin. So this is the difference. Here we have taken temperature difference and here we have taken temperature of the body. In that case, this will be the graph, and in this case, we are having the graph passing through origin. This is the only difference here. We have the temperature of body and here we have the difference of temperature of body and the surrounding. So rate of cooling is having this two graph where we have the temperature of the body and then difference of the temperature of the body. If you write the rate of cooling over there, it is how we can say rate of cooling. Here rate of cooling is called minus of dt by dt. This is called rate of cooling. And this is directly proportional to T minus of T naught. This is Newton's law of cooling. That what he observed, that whenever we have any liquid body and its temperature is not that much difference with the temperature of the surrounding, then what the rate of cooling will be, it is directly proportional to the difference between the temperature of that liquid and the surrounding. And once you remove this proportionality constant, proportionality here, there will be called one proportionality constant. This is dt by dt. This will be alpha times T minus of T naught, this one. So this relation, you can see it is, this is the straight line relation. Here we are having dt by dt. If you go for then T minus T naught, alpha is the slope over there. So if it is passing through the origin, then we know that it is y is equal to mx format. A straight line graph will be there between the rate of cooling and then temperature difference. temperature difference. So few results are there on the basis of Newton's law of cooling. That result I am writing, and these are the result which is used to solve the question. So what is the result here? You can see this is differential format of temperature here, and here two variable and one is time. So once you take both variable separable method and go for the integration, then you will be having the result between them. So it is exponential result you will be having. So I'm writing that result. First result I'm writing here, that what the T final we will be getting here, this T final will be, it is T naught plus, this is T initial minus of T naught e to the power of minus alpha T, where T I is your initial temperature, and Tf is your final temperature. Tf is your final temperature. Final temperature at t time it is, at time t. So at time t, this is the final temperature. Where is time t? Here it is time t. Alpha is the constant which we were having that relation, here it is. So once you write this relation in the form of this one, it is, I'm not writing that one and don't have that much time to solve this one, but I'm just showing you so that you can solve by your own. It is alpha dt, and then you have minus sign here, and alpha is constant, so integrate, this is 0, and this is having t initial, and any general time it will be t final. From here this result I have written. Okay, then next point, what you can get from this another format, that sometimes this form will help you. So another form of this one is, what another form I can write here? I'm just removing this exponential function and wanted to write it in log format. So easily you can make it into log. So it is alpha t, and this will be log. Then we have in numerator, it will be ti minus of t naught, and in denominator it will be t final minus of t naught. So this is from this relation I have written here. You remove the exponential and make it into log function. So here this will be the relation. The third form in the Newton's law of cooling is, this is a rate of cooling minus of dt by dt in terms of when it will be that specific heat will be given to you, and emissivity term will be given to you. In that term, how you can write? So this is 4 epsilon a sigma T naught to the power cube divided by mass, and then a specific heat, then T minus of T naught. Here S is the specific heat, M is the mass of that liquid, and A is the area. Sigma is the constant, T naught is the surrounding temperature, epsilon is the emissivity. So I'm writing everything here, that M is mass of the body, S is a specific heat, it is, then A is surface area, and E is, this is emissivity. So this form you can use to find the rate of cooling whenever we have a specific heat area and T. This result we can use. And the another approximate form what we have is this. This is also another form. This is the fourth form I'm writing here in case of Newton's law. These are the result which based on the Newton's law of cooling only. Another approximate formula I'm writing here. So this formula is mainly talking about the difference of temperature. Here it will be, this temperature will be mentioned T1 and T2. Likewise, in that case, you can use this. If I'm using temperature difference, it is from T1 to T2. So what is the difference in temperature? It is T1 to T2, rate of cooling, divided by the time T. And this will be equal to alpha. This is average formula. It is called T1 plus of T2 divided by 2, and then minus of T naught. So this form, you can see this formula can be considered to be when we have the temperature, body is cooling down from T1 temperature to T2 temperature in the interval of time T. So it is, you can say here that the body is cooling from T1 to T2. If it is cooling from T1 to T2 in the in time T, then we use this formula where the surrounding temperature is T naught, where surrounding temperature is T naught, surrounding temperature. And this formula, based on this formula, J main asks, J advance asks. So that is why I have written here. This formula is very important whenever you have given some time interval and the temperature difference and the surrounding temperature directly, you can use this relation for that one. Approximation method I have used and I have written the formula it is. And there is one graph also which is very important related with this only. The graph between L and T, this minus of ln format graph it is. So what is the temperature and the temperature difference relation with the graph? You can see here. So on a y-axis, we have, this is one of the graph, and directly they can ask you this graph. So this is time graph, and then in numerator we are having, this is, this I'm writing here, ln t minus of t naught. So this is the graph from their initial only. You can see that that is the graph you'll be getting t minus of t naught ln format, and then time, it is time graph. What kind of graph we'll be having in this case? This graph will be like this kind of graph you'll be getting. This kind of, it is a straight line kind of graph. And what is the initial value here? It will be ln and then T1 minus of T naught. T1 is the initial temperature where we are having. So this point is on this y-axis, it is ln T minus of T naught, and here we have T. So from this relation, you can see this is the graph. They can ask you that between ln T minus T means temperature difference between the surrounding and the ln of that one and the time T. It is, the graph will be. So this is the straight line graph you'll be getting. So remember these two relation, approximation and this graph, it will be helpful for you. I think that you will get a question. Maybe they can ask you this format question also, or this question format also, because Newton's law of cooling is very important for the point of view J advanced, for the point of view J main also. So these are the only formula from where they can make the question, and you can be asked the question. Okay. Next format in the Newton's law of cooling is, this is just formula only I'm writing here. So this kind of question may be asked, that thing I'm writing here. If temperature of a body changes from θ1 to θ2 in time t, and again, and changes from θ2 to θ3 in next time. When this kind of question will be there, that if the temperature of body changes from θ1 to θ2 in the time interval t, and then again changes from θ2 to θ3 in the next time, then you can use this one, θ2 minus of θ0 divided by θ0 is the temperature of the environment or surrounding. This θ1 minus of θ0. This ratio will be equal to, you can write it as θ3 minus of θ0 and then θ2 minus of θ0. So this ratio will be equal, where I have written this θ0 as the temperature of surrounding. Temperature of surrounding temperature. So this is one of the result which I have written directly, and the next result you have sixth. If equal masses of two liquids having same surface area and finish means same kind of a structure it is. So whenever we have equal masses of two liquids having same surface area and finish, cool from same initial temperature to same final temperature with same surrounding. Whenever this kind of question will be there, that it is question may be complicated in language, then you can use this result directly and you can save your time. If the equal masses of two liquids having same surface area and finish cool from same initial temperature to the same final temperature with the same surrounding, in that case we can use this T1 by T2 is equal to K2 by K1 and is equal to, there it is S1 by S2. What is S1, S2? S1, S2 is the specific heat. S1 and S2 are specific heat. So this will be the also one format in case of when we have the Newton's law of cooling. This remember always. Uh, if you remember result, it will save your time and you can attempt more question over there, because those students who are just deriving the concept over there in JMN exam won't click that much questions, but those students who have just remember the formula only and the concept it is, they can start with the direct from there only, no need to go for the derivation and save the time. Once you save the time in your exam competition over there, definitely you will be leading. Many of the student is not having that kind of ability, so that they have great mind, so they derive there in examination, they don't remember. Obviously it will be. So next point we have, next concept which you need to remember is, that is Wiens displacement law. See, this is Wiens displacement law, mainly talking about the temperature and then wavelength. It is this law states that the wavelength relation with the temperature. Let's see this. The wavelength, you know that wavelength you must have heard in that SHM, and in case of wave also you must have learned that one. So wavelength corresponding to maximum intensity maximum intensity of for a black body is inversely proportional to the absolute temperature of the body. So this is only law, and on the basis of this law, you can write. We have written here this wavelength corresponding to the maximum intensity. Maximum intensity. Yes. So for that time, what the value of lambda we are having, that lambda, you can write this lambda m is directly inversely proportional to the temperature, and once you remove this proportionality, there will be one constant b by t, it is, where b is called Wiens constant. This is proportionality constant here, that is called Wiens constant. And on the basis of this, we have some few results that you can say B value will be fixed. It is this value is 2.898 into 10 to the power of minus 3. And then here we have this, the unit of this will be here meter, and this is Kelvin. So it is meter and then Kelvin, meter and Kelvin. So whenever we have that emissive power graph with the wavelength graph, in that case, you'll be getting area under that graph. And that area under that graph will be, it is called total emissive power you'll be having. So we can have that graph also, and how you can relate over there. Just we'll see in the next section that how you can relate over there. Let's see this. So few results based on Wiens displacement law I'm writing here. What are the results? Do you have one result? First, you have this graph. This is the graph between, on the y-axis we have, it is a spectral emissive power. A spectral emissive power. On a y-axis we are having this, you can represent with the E times of lambda, like this it is. And here we have lambda. So the graph will be this kind of graph I'm making here. Let's see if the graph is this kind of one graph it is. You can see the another graph. This kind of graph it is. So at particular case, you can see here this, if I'm considering this point to be the maximum on this curve, you can see here I am considering this lambda as lambda one, and this area you can get here this rate. The area which will be this zone, it is this, these are the area part you can calculate over there. So we'll think about the area also next. And let's suppose this area I'm considering bigger one as A1, and this smaller area is A2. This is the area relation here. And in this case, we are having temperature T1. And in this case, we are having temperature of T2. Two graphs I have made. This is for one graph and this is for second graph. So here in this case, you'll be having maximum wavelength. Here it is, that will be somewhere at lambda 2, lambda 2. So how you can relate the lambda 1, lambda 2, T1, T2, A1, A2, that is there. So you can see the lambda and T are inversely related. So once it is lambda will be maximum, in that case, the temperature will be minimum over there. So you can relate here when we have that relation, that how we can relate with lambda 1 with the result lambda 2, the second graph it is. It will be inversely related, so it is T2 by T1. This is one relation you are having with lambda and temperature. Then the second relation you are having here, it is A1, area of cross section by A2, A1 by A2. And we know that it is temperature relation with the A1, A2 when it is given to aspect power relation it is. So it will be related directly proportional with a T to the power 4. So it is T to the power T1 to the power 4, and here it is T2 to the power 4. So these are the result which you can remember if you can easily solve the question. Complicated or difficult, like in exam, a student feel that this kind of question is, sorry, this is the difficult one question. I can't solve this question in examination, but it is only difficult that when you don't remember the formula or you don't remember the concept. If you remember, then that is not difficult for you. Easily you can solve over there. So this is the these are the two results which I have written based on the graph. And the third result I'm writing here, what the area will be there. Area under E lambda and the lambda. E lambda means it is emissive spectral emissive power. Here it is spectral emissive power and the lambda graph. If you will get the area under this graph, this is the area you'll be getting here. It is sigma t to the power 4. Sigma t to the power 4. This is what it is called, total emissive power. Total emissive power. So sigma t to the power 4 you'll be getting. Now you can see here that if the temperature of the black body is temperature and the lambda is inversely related. So if you increase the temperature twice, the lambda max will become half and the area becomes 16 times over there. So this is also one of the relation that you have to remember, that if I'll this fourth result I'm writing, if we increase the temperature, if temperature of black body is made twofold over there. If we made twofold over there, then lambda max become half. This is one of the result. And while area becomes, because of this twofold, it is the area is proportional to t to the power 4 here. This sorry, area is proportional to t to the power 4. So you are making it is twofold. So what is 2 to the power 4? It will be 16. So it will become 16 times. 16 times area will be increased over there. So once you are changing the temperature to twofold only, lambda max becomes half over there and the area becomes 16 times over there. So this is all about the Wiens displacement law, and it is talking about the wavelength and the absolute temperature. And there is one constant also there, and we can have the relation between area of cross section and temperature, and that is it is T to the power 4, absolute temperature to the power 4. And also you have one relation which is really important one. That relation is the third one. This you need to remember, that what is the area under graph of this one will be, it is sigma T to the power 4, and that is called total emissive power over there. So these are the result which you need to keep in mind. From there we can have this what you can say, the question maybe J main, J advanced. You can see the question. You'll be getting the from there on here only. You'll be solving all kind of question over there. Then the last part of this, what it is, Wiens displacement law, we have to measure the temperature of the sun. So this is the last part of this concept today. So what you can say here, this is how to measure the temperature. What are the relation temperature of the sun you are having? Temperature of the sun, So this is the last topic I'm discussing in this section. So what is the temperature of sun? How you can relate it with this is what you can say, total energy radiated by sun per second. So if I'll suppose to have suppose this is the sun here, and sun radius I'm assuming here r. R is the radius of sun. The sun it is. And from sun, let's suppose some distance we are having, r is the distance where I'm considering here. In the same line joining, there is one planet. Planet I'm considering the Earth it is, because we are the concerned only. So to understand the things we are considering Earth here it is. So this is sun here and then Earth here, and the distance between sun and Earth it is r. Okay. Now if T is the capital T is the temperature of sun. So this is temperature of sun. I'm assuming temperature of sun as capital T over here. So you can say here that the total energy, or you can total energy radiated by sun per second. So when I say that energy per second, it is power only. It is power only. So what we have written in the power formula, you must have remembered that one. It is sigma T to the power 4. And then we have area of cross section of that one. So it is 4 pi r square. So this is the area 4 pi r square I'm considering here. of the area of the sun body, and then absolute temperature T to the power 4, and sigma is the constant over there that we know. So this is what you can say intensity at a distance r from the earth. What will be intensity over there of the sun radiation is happening. So what the intensity on the earth, this radiated power, or what you can say, this is energy radiated by sun per second. So this much energy is radiated by sun per second. This much energy is radiated by the sun per second. Per second, sun is radiating sigma T to the power 4, 4 pi r square. Now, coming to the earth, the intensity, coming to the earth, the intensity at distance r, distance r, distance r from sun. Maybe if you can, this r you can consider for the another planet also, that will be there. But right now I'm considering just earth only. So the intensity at a distance r from the sun, that is on earth I'm considering, that is on earth I'm considering. So this intensity can be written like power radiated per unit area. That is the intensity. Very first time I told you that it is energy per unit time per unit area. That is called intensity. And this is the intensity at a distance r from the sun. That is on the earth what we are getting here. What intensity from the sun we are getting on the earth. That how you can calculate that intensity. So it is sigma T to the power 4 times of r square. And here this area of earth, I have to consider this is the area of earth. So it will be 4 pi r square, and in numerator also 4 pi r square. So I'm writing just r square here only. So this only r square. 4 pi is in numerator, it was that 4 pi, and in denominator also 4 pi. So 4 pi get cancelled out. So this is the intensity what we are getting on the earth from the sun. So this ratio, if I supposed to write this ratio as capital S, this is called this S is called solar constant. This S is called solar constant. And this S value is calculated over there that it is 1.4 kilowatt per meter square. In 1 meter square, it is 1.4 kilowatt. You can imagine this is the solar constant, or this is the intensity what we are getting at the surface of Earth. So from here, you can calculate the temperature of Earth also. So how we can calculate the temperature of Earth? So you can see from this relation only we have T and intensity solar constant here we are having. So with the respect to solar constant relation, we can calculate the temperature of the sun. So how we can calculate the temperature of sun? You can see here, this is T is equal to r square by capital R square. Then it is multiplied by S divided by sigma, and then it is power, its power will be 1/4. This will be the temperature of sun. This is temperature of the sun. Temperature of the sun. How we can find out this? These are the result which we know that what is the radius, what is the distance r, capital R is the distance between sun and the earth, that we can write over there. Then radius of the sun it is, then solar constant, then sigma value. Once you write all the data, you'll be getting the result. So I'm writing the data on the basis of that. You can find out approx method, approx temperature. So distance from the sun to earth we are having, it is 1.5 into 10 to the power of 8 meter. And then we are having that radius of the sun, it is 7 into 10 to the power 5, that meter it is. And then we are having solar constant. Just now we have seen it is 1.4 into 10 to the power of 3. And then we are having sigma, it is 5.67. We remember it, 10 to the power of -8. So this is the relation here we are having. So 1/4, if you do it, if you simplify it, once you do the calculation over here, we'll be getting approximate is 5,800 Kelvin. So approximate, you can see this is the temperature of the sun. On the basis of that, we have calculated this is. So this, I think this is the complete segment. What you need to remember for the radiation chapter is, once you can go faster, it is radiation. I have written here. It is the heat fastest method directly from a medium is not required. Radiation is fastest, and all bodies can radiate the energy. All body can radiates energy. All body can radiates energy at all temperature, because we know that the temperature of the any body may be greater than 0 Kelvin only. So radiation process you cannot stop over there. So for perfectly black body, it absorbs radiation incident on it, and the perfectly black body absorptive power, then emissive power, then emissivity. Stephen's law. Stephen's law is mainly talking about radiation of from any hot body it is. So it is directly proportional to the radiation. Means I'm talking about that radiant energy emitted by the perfectly black body is directly proportional to T to the power 4 radiation emitted in radiant energy emitted per second per unit area. That is. So from there you can write the power and area relation with the this one. Power by area only, it is called intensity, and from here we have been for black body, and for other kind of body here. Then rate of heat loss, how it is when system and surrounding temperature will be given to you, this relation. Then rate of cooling, this I discussed. Newton's law of cooling, we are having this graph, two graph and this relation. Then a few results I have written on the basis of Newton's law of cooling, and on the basis you can relate any form maybe there in the J main and J advanced. From here only it will be. So if you remember the formula over here and the concept, you will be getting, you can solve by your own. And then I think this is the complete heat chapter we have discussed. In this case, here it is. So the complete heat chapter is completed. Only thing we are having now remain with that, it is kinetic theory of gases and the thermodynamics part. So it will be covered in the next video, that kinetic theory of gases and the thermodynamics part. So I hope you understand this radiation topic. Thank you.